record the meeting. Yeah. Okay. Hello, everyone. To this session of the FGC IPM number theory webinar series. Today's speaker is Dr. Shabnam Akhtari from University of Oregon and Cornell University as well. And she will talk about monogenic cubic rings and Thue, if I am right, and Thue equations. And thanks, Dr. Akhtari. You may start your talk whenever you want.
Thank you so much for invitation for all of people in organizing committee. It's very, very nice of you to think of me. I'm really happy to be here. We were talking about Tehran traffics and how bad it is, so we just saw how real it felt like as if you're waiting for people to arrive. It's a pleasure, of course, to talk to you, and also it's also sad to know that it's just all the travels are impossible, and for me it has been such a long time not being around there. Also, I'm so happy to be joined by some people from Turkey, Istanbul, Ankara, and anywhere else. I saw some other friends' names, so thank you so much for being here. It's nice to see some familiar names and also meet new people. Thank you so much, and thanks for organizing this. I'm sure it's not easy, and I'm sure it's very beneficial for many of us, especially younger mathematicians. So today I'm going to talk about monogenic cubic rings and Thue equations. So I want to say that this talk might not be like there are not that many new results. What I'm trying to do is to connect some different areas that maybe the connection is not very talked about. And two equations are some sort of Diophantine equations that I will shortly define, but those are the center. Those have been the center of my research. And what I'm trying to establish today is just to show the connection of particular two equations to these monogenic rings and just explain that why I have to work with cubics. Of course, you can work with quartics too, but then after that, it's just really you need new methods. So again, not many new results, it's mostly understanding the application of the Diophantine equation in some algebraic in structures. So let me just be more clear what we mean by a monogenic order or ring. So mostly I think in the context of number fields, but generally you can think of any cubic ring with one. So in a number field setup, we call O an order. I show it with O here. We call it an order if basically it's a Z lattice, but at the same time the elements of O over Q have to generate K, so it's a full lattice in K. So the ring is called monogenic if it's generated by one, it can be generated by one element. So and many times actually it turns out that rings are not monogenic in number fields, and generally cubic rings cannot be generated by one element. So a ring is called monogenic if it's generated by one element. And in the talk, sometimes I call this kind of element monogenizer. So it's just not a really word that is used very often. It's a newer word that people use to describe this kind of. So alpha is monogenizer. So the kind of questions we would ask if there is a monogenizer, if there are, how many, is there another element like beta that can monogenize the same ring, and so on. So as an example, for example, something if you do a little bit, if you are even a little bit familiar with algebraic number theory, you have a number field, then you have the ring of integers. And what we know about the number fields is that the number field, a very nice property is that you can always find one element that generates the whole number field. And there are so many elements of this sort over Q. And O sub k is the ring of integers of the number field, and this is actually the maximal order, the biggest order that can exist in your number field. And here is the question: is there any alpha, or let's call it beta this time, such that Q, the ring of integer is Z beta. Of course, if such beta exists, then K has to be generated over Q by beta 2, but this is not the case most of the time. And most of these things are conjecture at this point. We believe that most of ring of integers or most of number fields are not monogenic. But I will talk more about results, more recent results about cubic number fields. But the conjecture is that this is too much to ask. This is not happening most of the time, right? All right. So then here is the big, very important question. Is a number field monogenic? By that we mean, can be the ring of integer as an order, is it monogenic or not? And then other questions is that if you have any ring in your number field, let's say, is that monogenic? If it is, how many monogenizer it has, how they are related to each other, and so on. So these are the questions that I will be interested in. We do know some results about that. For example, in the 70s, Kalman-Giuri proved that if you have an order, then in a number field, it has finitely many monogenizations or finitely many monogenizers. And I have to be careful when I state that. For example, as a quick observation that if a ring looks like Z alpha, then that alpha plus or minus any integer would generate the same rings, right? If I add a as integer to alpha, it would be the same ring. So of course I want to count alpha and alpha plus minus 1 and plus minus 2, all of them as the same monogenizers. So in that sense, we are talking about non-trivial monogenizers, and two monogenizers are the same if their difference or addition, even z of negative alpha would be the same. Their difference or addition is an integer. But other than that, if they are not essentially the same thing, we are counting them as different. And this very, very deep result of Giuri, not obvious at all, proves that there are finitely many of them. And for any given ring. Another result that is due to Giuri and Evertse about a decade later actually quantifies that, and they try to count the number of possible monogenizers. And here is the number they get when n is the degree of your number field. So it's not even, I can't even call it counting, because they cannot really count how many. They say there are at most this many. So it's an upper bound that we believe is actually not sharp at all. One should do much better than this. But I want to say again, this was impressive that they could get any sort of finiteness result, and all is coming from techniques from unit equations and how you do that. Unit equations are very classical equations in Diophantine number theory. I'm not going to talk about them, but it's very simple. Basically, you write a x plus by, a and b probably you can take them as integer equal to 1, and then you ask if there are units x and y in your number field that satisfy this equation. And very simple equations, but extremely hard to understand, and especially count the number of solutions, just because you go to number fields and then these are units and you have this rich structure of units and number fields, and there are lots of structure, but also especially computationally and algorithmically, it's quite difficult to understand their size, and like there's a nice group structure, right? But other than that, you just don't know how they come in and create more solutions for you and how to control them. So this unit equations have been really the maybe in some ways, not exaggeration to say, the only way to think of rings and their monogenizations and monogenizers, right? So my goal in this talk and some work that I have been doing recently is that for rings in number fields of lower degrees, like 3 and 4 specifically, find other ways that we can give upper bounds that are better than this thing that comes from unit equations. And really, it's not easy. And as you said, unit equations are the to-go thing here. But again, if degrees are lower, well, maybe there is hope, and I will hopefully convince you that yes, in terms of cubic there is hope, and then you will believe me that in terms of quartic there is hope too. Here I wrote a result of Iverson more recently, that he improved their previous result further. Still, he gets a very large bound, like something exponential in like in n squared. So again, we are hoping for much smaller than that. Okay. So n again is the degree of your number field, and O is just a ring, any ring in that. Let me just remind you that orders in quadratic number fields are very well understood. Basically, they are parameterized by their discriminant. If you write down a number d, that can be the discriminant of a quadratic ring or number field, you can write a unique ring that has that discriminant. Everything is parameterized by one integer, and every other ring that you could write with the same discriminant is going to be equal to this. And so it's just or if you are leaving the number field case, your ring would be isomorphic to this ring. I'm sure many of you are familiar with the definition of the discriminant, but I want to just remind you that, because soon I talk about discriminant forms that are coming from this definition. With the quadratic case that I just discussed, if you have a quadratic polynomial, the discriminant is our beloved b squared minus 4ac that we are talking about, like since we started doing math, basically. But I wrote in this on this page, I wrote the discriminant for a binary form, a form in two variables, x and y. But if you want a polynomial, just put y equal to 1 here, and then basically you get the discriminant to be the leading coefficient to the power 2 times d minus 1. D here is the degree of your polynomial or binary form. And then the rest is really coming from the difference between two roots. So every two roots, you take their difference, and then here I just didn't want to, I just have I greater than j, so that once I count for alpha I minus alpha j, and another time alpha j minus alpha I. So this is the discriminant in general. There are important properties of discriminant. One thing you see, it actually kind of measures how complex or how complicated, let's say, your polynomial is, and mostly it tells you not everything, but something about the distribution of your roots, right? Like, for example, if you have repeated roots, right away the discriminant would be 0. So the discriminant is interesting when you don't have repeated roots. So when you work with irreducible polynomials, which are going to be important when I think about the minimal polynomial of algebraic numbers. Another property that I will talk more about this, is that they are invariant. So if you do some sort of unimodular substitution in your form, you get a form with the same discriminant. But for now, just think of it. I don't expect you to memorize this formula, but have an idea of that. That's basically a constant coming from the leading coefficient times the differences of any two roots. And here is how the discriminant of a discriminant form is defined. Okay, remember, we have a number field. Another beautiful property of number fields is that they possess, each number field has an integral basis, meaning that you can always find the number field is of degree n, and you can always find n q independent elements in K, such that K is spanned by this over Q. But at the same time, these integral bases has this beautiful property, again, we learn in elementary algebraic number theory, that if you want to read off all of the integers, algebraic integers in your number field, this set is going to help you, because instead of allowing the coefficient to come from Q, just restrict to Z. So that's a very, very beautiful discrete way of understanding the ring of integers. So okay, in this case would be Z 1 omega 2 omega n. And that is very fundamental in defining a form that is we call discriminant form. What we do is, again, we think of every algebraic number in an algebraic integer as a generic algebraic integer. So if my basis was 1 omega 2 to omega n, then I just imagine x1, x2 to xn as coefficients, that whatever I put there, that gives me an algebraic integer. Now let's write the discriminant of that. Okay, but then what if I treat x1, x2 to xn as variables? That will give me a form in n variables, and I know that once I put this algebraic integers, then any integer value for x1 to xn, I get an algebraic integer. And this formula that I wrote here, that should give me the discriminant of that algebraic integer. There is one little thing I missed, but I really didn't. Here, I kind of ignored x1. Why did I do that? x1 is the coefficient of 1, right? So if you take the discriminant, then it doesn't matter what integers you have, like x1, like if you put 5, 10, 12, whatever. Why? Because when you find the discriminant, look, you look at the difference of algebraic conjugates, so that gets cancelled. So what did I do here? I just reduced the number of variable just by 1, because the variable that is corresponding to 1 does not contribute to the discriminant, and that should ring a bell, because it's very similar to index of what we talked about in the generators of the ring. So if you have Z of alpha, it's the same as alpha plus A, and you will see that coming out of these formulas. Okay, so anyway, so the discriminant form, if in a number field of degree n, is going to be a form that can be defined for any fixed set of integral bases, and it can be written in n-1 variable. And if you define, you can have different set of integral bases, obviously, but your form and the coefficients of the form and everything would depend on that. But eventually these forms in some sense are equivalent, so you are not really you are not committed to any integral basis, but it's good to fix one and work with that. So something to mention, but easy to observe, is that if you write a discriminant form like this, of course the coefficients are coming from this omega 2 to omega n's, but the coefficients end up being integers. So that's how discriminant form, the way I'm going to clean up here a little bit, in the way we define, is going to be actually a Diophantine equation, in the sense that it has all the coefficients integer. So if I ask you, if I write an equation like this with a fixed integral basis, and then I put it equal to D and ask you find the solution, so you are going to go out and look for x to xn that are integers. But actually what you are finding are algebraic integers in K that have discriminant D. And this is a quite difficult question. That is, we don't have clear answers to that. It's just that it's asking you how many elements in a fixed number field, or what elements, more than how many, what elements in your number field have a fixed discriminant. And we do have finiteness results again. There are finitely many up to some sort of equivalence, but we do not, we can't count them. It's just a very simple question. It's just there is an equation with n-1 variable integer coefficients equal to an integer, but it's really not always possible to count how many solutions they have or so. Another thing we learned quite early in any algebraic number theory course, and it's just the really how the discriminant is defined. If you pick a number, and here I didn't really define that, but the discriminant of an algebraic integer would be calculated through the discriminant of its minimal polynomial. So the discriminant of an algebraic integer is always the discriminant of your number field. Again, I'm sure many of you know what it is, but if you don't know what is the discriminant of the number field is very related to this, but it's a fixed thing for the number field. It doesn't depend on every individual element. Times a quantity that we call the index for good reason, so I alpha squared. And you can see why we get something squared from my definition. Remember, in the definition, I had all this alpha I minus alpha j squared. So there is something that called the index of alpha, I of alpha squared, and times some constant. Okay, again, these are all proven in algebraic number theory. I think that's algebraic number theory is, I mean, maybe it's very personal opinion, this beautiful course you take, but there is a time throughout the first semester you do that you have to handle very ugly formulas with these matrices and multiply them and find the determinant. It just doesn't fit there. And I never kind of enjoyed that part of algebraic number. It's just not fitting for such a beautiful subject. But right now it's amazing that it's very much into this formula, and it's just creates new problems. But anyways, if you remember those formulas that were not fun, that's what I'm talking about. But this quantity that is squared is actually a very, very important quantity. As I said, it's called the index of alpha, but it has a very important meaning. I of alpha is the index of z joined alpha in your ring of integers, okay. And when I say index here, I mean the module index of that. So if I call this, maybe let's call I of alpha. It's an integer, so what it means that if you take any algebraic integer like beta, so beta is in OK, then and multiply it by this integer, then certainly that belongs to Z alpha. Okay. So when I say I of alpha is the index of Z alpha, it means that as a module. But this is exactly the question, the big question, I called it the big question that I was asking before, that if I want to see if OK as a Z module is monogenized or not, what I'm really asking is that if there is any alpha that I can write it like Z join alpha, but what I'm really asking is that whether I can find an alpha such that I of alpha is equal to 1. So this is all I'm asking, whether I find an index 1 equation, right? But many times, as I said, it's conjectured that we don't find index 1 things, but it can also tell us how big we can get with monogenized orders. For example, if we have OK, and other questions that some people really are considering very seriously is that what is the smallest index you can have? So what is the biggest lattice that is monogenized but covers as much as possible? So if you have that index 1, then you have a monogenized number field. But if you don't have, then still you want to know how close you can get with a monogenized order. Okay, so let's go back to our discriminant form equation. It's the one that I showed in the previous page. But let's bring this I that we introduced here. Can be written as a form again, obviously, because we have a beautiful integral basis, and we can think of any algebraic integer as as its integer coordinates for that integral basis. So the the discriminant form becomes something that we call index form, square times the constant that is the discriminant of your number field, okay? And hopefully you are convinced now that solving index form equations can tell me a lot of things. By equation, I mean if I call this my index form, and then if I put it equal to 1, if you can find a solution, we are very happy, we found the monogenizers. If you put if you solve I of x to xn equal to 5, and you find all of the solutions, you have found all the possibilities for alpha that generates an order of index 5 in OK, right? So generally, in any number field of degree n, this index form equation, as we observed, has n minus 1 variables, and the degree would be n choose 2. Any questions so far before I go to more specific case cubic? If the definitions are clear. All right, so again, remember these numbers. I didn't really show you this n choose 2, but it's really quick calculation with the definition of the discriminant, how many factors you have and so on. But all that matters is that all that matters to me right now is that when I'm working with cubic number fields, I have two variables. So x2 and x3, and x1 is missing because that's the integer that doesn't contribute to the discriminant or index. And then I have n choose 2, which is 3 choose 2, 3 as the degree of the index form. So the degree of I is also going to be 3. And then if I talk about any index form equation, I'm having I of two variables equal to one integer. This is a Thue equations that I have not defined yet, but I will tell you more about. So this is basically a cubic Thue equation, a Thue equation of degree 3. And again, the relevance for me personally comes from the fact that I have been working on these kind of equations a lot. But the more important reasons why one should consider this in this case is that we have more ways of understanding Thue equations, and there are more hopes of, especially when you have a smaller discriminant, let's say, there are more hopes of actually getting magma to solve that for you and find your solution. So I personally don't do computations, but for people who are really looking for creating monogenizers, once they have Thue equations, and if the discriminant is small enough, they can actually calculate them these days. And this is something that is not established for bigger degrees just because you don't have Thue equations there. Let's define a Thue
Sorry, I
equation.
have a question.
Uh-huh.
Sorry. What was the small I
Oh,
in the
that
Thue
one
equation?
for me, it was just an example. You can put any number. You're asking about this one, right? So I'm just saying that you have a form that we define, and I put it equal to any integer. So I was for
It's
integer, yeah.
arbitrary, yeah?
Yeah. But for any fixed integer, you get a form and you can think of solving it.
Oh,
If you put 1, you're asking a lot. If you have if you have solutions, we are very happy, but many times you don't. But now that you ask this question, let's just talk more about this. If you do 5, and if you could find solutions, x2 and x3, then you will, let's say that you get, I will call alpha 1, alpha 2, alpha k. If these were all the solutions that came from your x2, x3, and that you found for this one, for the value of I equal to 5, what you have, you are making z alpha 1, z alpha 2, and so on, z alpha k. All of them are going to be orders in your number fields. Obviously, they are in your number fields because they come from that integral basis. And all of them are going to have index 5 in OK. But another question that I hope to touch at the end of this talk is that which one of these are the same rings and which one of them are different rings. So which alpha i's that you found as solution to this gave you the same ring, because you can have several different rings of index 5, let's say, but which one of them are the same, which one of them are not.
And with the fixed index,
Uh-huh.
yes?
Yes,
And
that was
any
5.
others?
Yeah. If you get two rings, they have, if they are the same, of course they would have the same index. But then the most difficult problem here is that if you got several rings, which one are the same? Because there could be rings that have the same index, but not the same. They are not the same. Yeah, perfect.
Can I ask a boring question?
Sure, go ahead.
So is it easier to solve this for 5 than rather than 1?
No, 5 was just my integer example.
No, I'm just saying that, no, I'm just saying that are some numbers easier than, I mean, is number 1 the hardest case, or
I
doesn't
think
really matter?
in general doesn't matter, because if I look at a cubic equation equal to an integer, it's very hard to know just by looking at it if it has solutions or not. But if you have a specific one, for example, if you know the coefficients of the form I, then it really depends on some p-adic behavior. For example, you might have local problems to have that equal to 5, right? So but in general, no, 1 and other things are not different, but there are more results for equal to 1, but it doesn't mean it's easier to solve the equation equal to 1. It just means that we can reduce the general questions to equal to 1, but then all of our results is that if this has any solutions, then this would have or not. But the simple answer to your question is that none of them is easier than others in general. But obviously, if you have something that is not equal to 1, you can have um, you can have local obstructions, so, and for some obvious reasons not have solutions. On the other hand, if you don't have obstructions, you have more possibilities for trying x2 and x3. So that doesn't mean it's easier or harder. That just means that just means whether the possibilities of solution, the statistics of that. So, and again, in general, the the conjecture is that a random two equation does not have any solution. But we do know two equations that have solutions. And like, for example, one of the results, I will mention it, one part of it later, one of the results is by myself and Bhargava, that we prove that a positive proportion of two equations do not have any solution. And in our result, even though we just focus on one, but all of the methods can be generalized to any given integer.
Great, thank you.
So yeah, that was actually a very, very nice and important question, and we don't know the answer to that. But in general, no, what you have on the right side of the equation cannot make it harder. But when you work with the specific examples, obviously it can make it easy. Okay. So what is the two-way equations? Generally, when you want to write a two-way equation, what matters is that you have two variables. So you work with a binary form, right? And once you have a binary form, if the degree is at least 3, and I will assume it's irreducible. Irreducibility is not important, but it's simpler to assume it's irreducible. If it's not, then you can consider irreducible factors, and then at the end you can come to an integer and see like how many solutions you can have for each of them and so on. So it would be a combinatorial problems more than number theory. But anyways, if you assume that your degree is at least 3 and your form is irreducible over Q, then Thue in 1909 proved that if you put f of x and y equal to m, where m is any fixed integer, you can have only finitely many solutions, okay? So, and the degree 3 here probably is so quick to know why it's important. For example, if you have degree 1, you have a line. Obviously, on a line, you can have several, like infinitely many integral solutions, x and y. If you have degree 2, you have quadratic equations. For example, in case of Pell equations, you have seen examples of infinitely many coming from the units of your quadratic number field. But the degree has to be 3. And then, of course, irreducibility is that you don't want to have a line to the third power, or a Pell equations to fifth power equal to 1. So you want to have 3 different linear things over linear factors over C at least. So that's the whole thing. But for simplicity, I'll talk about irreducible ones. So like what we did here in the index form equation for cubic number field, we actually had a Thue equation simply because it was cubic. The discriminant is not 0. So in this case, I was irreducible, and we are putting it equal to an integer. Most important integer for the big question whether OK is monogenic or not is 1, but we can talk about indexes of other rings by putting I different integers. So this is a Thue equation, and that's why I like to work with cubics. But why is it so important here? What's really the relation? The relation is the actual reason that Thue equations are important for cubic monogenic orders, but not for others, is that when you prove this is supposed to be, this page is supposed to show you how to prove this finiteness result. So what he did is that, okay, he said, okay, I have a binary form f of x and y, assuming it's not reducible over q, but let me factor it over c, okay? And here is the factorization. So what happens here is that you can divide both sides, for example, by y to the degree, and these are all going to go, and this is x over y, x over y. Let me move this a naught also down here, right? And what you have on the right hand side, you have a bounded, a small thing. You have your fixed integer m divided by a naught. If y is 0, you just quickly solve this, but we can assume y is not 0. But what you have on the right hand side is a small bounded quantity. So one of these xy minus alpha i's on the, at least one of the x over y minus alpha i's on the left hand side has to be a small. They can't all be big. But I'm vague here how small or what it means. But anyways, to edit a little bit of analysis here and realize that one of these factors on the left hand side has to be a small, so that x over y as a rational gives a good rational approximations to one of these algebraic numbers alpha 1 to alpha d. And then he used his results, that was improvement of Liouville's approximation of algebraic integers, to prove that there can be only finitely many such things. And then eventually he says that close to all of these alpha i's, each of these alpha i's, there are only finitely many rationals that can come from the solution of these equations. I have d different algebraic alpha 1, alpha d. So altogether I have finitely many. So, and what I want to emphasize here is that the work of Thue is basically the bridge between Diophantine equation, a Diophantine equation, and Diophantine approximation, the rational approximation. So if you had more than 2 variables, you couldn't do this proof. That there are beautiful things out there for more variables, obviously. But in 1909, that was what you had for 2 variables. And what I'm trying to say today is that for cubic orders, when I'm understanding their index, I can translate the problem to a early 20th century problem. And that's where we can get some results that are better than the results that the the general results, and very impressive general results that we have. Okay, so in cubic case, the fact that we have two variables that in our index form makes us like let us use use Thue equations and work with the Thue equation and use other results. So as I said, I have worked on Thue equations, especially cubic one, during my PhD, and then lots of people have good results on cubic Thue equations. I think Professor Qader Marzi is in the audience, if I'm not wrong. He worked on cubic ones, and so in many ways they are well understood. But the question is that which results can be used to understand this algebraic structure in number field that I'm talking about, the orders, index of orders, and answer questions about that. So, and not, by no means I'm going to cover all the results that exist. I'm going to cover a couple of important ones. In 87, Bombieri and Wolfgang Schmidt proved that actually if you have f of x equal to plus or minus 1, you can have a very good bound. The number here is not very important. What is important is that the bound does not depend on the height or the coefficient of f. It's general, it's uniform, and it's linear in the degree. So it's some constant times degree. And they also extended the result to say that what if instead of f equal to 1, I was looking at f equal to m, and they said, okay, if you have a good upper bound for that, which they did, they had c times d, you could take your upper bound and multiply it by the degree to the power omega of m, where omega of m counts the number of prime factors of m without multiplication. Okay, so, and why I wrote this way, because the result is really beautiful in the sense that if in the future, which it happened, like for example, I worked in improving their value of c. If somebody came and improved their general bound for equal to 1, the same bound could be used and multiplied to d to omega of m to give you a general bound. So you don't have to stay with their 215 times d. So that's why I wrote it that way. But I also wrote it that way just to tell you what they are doing. So what they are doing is that f of x and y, they start with f of x and y equal to m, and they think of m as multiplication of some primes, and these primes can have powers. I'm going to ignore that for a little while. And what they do, they are going to do some matrix, really matrix actions of f of x and y, and it's kind of very elementary, but it's a bunch of matrices I don't want to write, and reduce f mod each of these primes, and therefore they can cancel the primes in M. So they reduce f mod p1, and they get, for example, if we are in cubic case, at most 3 new forms, and then m divided by p1, each of them m divided by p1. And what they do, what's impressive in their work is that if there is a solution to this original equation here, they can track it to one solution to exactly one of these equations. And then they take this and reduce it mod p2. Again, they get at most 3 in cubic case, at most 3 equations after these matrix actions, and this time they get rid of their p2. And then this 3 that I talk about, or d that I talk about, it comes from the fact that f mod p can have at most d, where d is the degree roots mod p. So when you read all the coefficients mod p. So if it has 2 roots mod p, then they would get 2 forms. But since it can have at most d, these 3's are coming, and at the end, because they reduce mod every prime inside m, they get this d to omega of m. Okay, so And as I said, for cubic ones, there are better results than Bouvier-Schmidt, and because of this reduction mod p that I tried to explain, many people concentrated on equal to 1. For example, Mike Bennett has a very sharp result that says there are at most 10 solutions this is a Thue equations, I should say. And this is quite sharp in the sense that we do know equations that have 9 solutions. 10 we think it shouldn't be, but one solution is just extra. And then if the discriminant is large enough, there are results by Okazaki that says there are at most 7 solutions. Again, all the examples we know for Thue equations with many solutions are with a small discriminant. So this is pretty good too. So we have very good bounds for cubic Thue equations in particular. So moving back to what we were talking about, remember that I defined an index form equation for general number field, but in terms of cubic, it turned out to be basically a cubic Thue equation. I reminded you here where it came from. It came from the discriminant form and then divided by the square root of the discriminant of our number field. And therefore, to understand the indices I'm a little bit exaggerating when I say understand. It doesn't tell us everything, but it will tell us lots of things we didn't know. So an index form can be seen as a Thue equations. A Thue equation is something that comes from a cubic binary form. But the very, very important thing here is that every equivalence class of integral cubic form is just gives you actually a ring that way. Why? Because you can look at your binary form and realize it like that, and then this alpha I and alpha j, beta j will give you the basis together with 1 should give you the integral basis that you are looking for, right? So, and again, if alpha and beta, this alpha beta are the same as this alpha j, these are their algebraic conjugates, this ring Z joined alpha x plus beta y for any integer value x and y that you put in here, that would have the index equal to the f of x and y, because that's the index form associated to that. So, and this x and y, you have the freedom. You put any integer, of course you stay in your number field, and then f of x and y is the fixed value, fixed cubic forms that is associated to that. Let me quickly, because I mentioned equivalence classes of binary forms, I just, for those of you who are not very familiar, I say what I mean. So as I said, you can take a matrix and let it act on your binary form. And what you see, if you have f sub a to be defined that way, you get another binary form of the same degree. And if your matrix is integral, then when it acts on an integral form, then you get another one. Now, if the matrix was GL2Z, some people like to work with SL2, but for me, the fact that the determinant is plus minus 1 is enough. I want just to have an inverse in Z. So if A has an inverse, integral inverse, I call f sub A and f equivalent. Why? Because through these matrices, you can go back and forth. For example, if you looked at f equal to 1 as a solution and f sub A equal to 1, I meant as an equation, you can correspond the solutions by action of these matrices. So you can, if you count 5 solutions to this, you have counted 5 solutions. So there are like there is bijection between solutions. So I call 2 forms equivalent if they are equivalent under GL2Z action. And here is the results that I really are back there and they existed. So there are parameterization of cubic rings, not just in number field, generally due to Levy, Delaunay, and Faddeev. and more recently they have been generalized by Gangro-Sabin. And what they say is what I try to hand-wavingly describe, that isomorphism classes of cubic rings are in natural one-to-one correspondence with classes of integral binary forms. So you get a cubic ring, you can find a whole class, just one class, a unique class of binary forms that correspond to that. And
So the cubic ring is the ring of integer of a cubic number field?
For me, the cubic ring is for me, I think of number fields, any ring of any cubic ring in a number field. Yeah. But you can think of any ring, commutative ring with one. It doesn't have to be in a number field. It would be isomorphic to one of these, but that one is in bijection. So I think especially the earlier work of Levy, I don't think they work with number fields at all. It's just
So what is the definition of cubic ring?
So maybe different people have different definition, but definitely it has one. The ring has to have one. It's cubic. It means that it's generated by three elements, and then it has ring a structure.
Generated as the algebra, right? The
yes.
Z algebra.
Yeah.
Okay.
Z algebra. Perfect. Yes. Yeah. And that's something that, of course, I can prove now, and it's hard to prove. These people did fundamental work, but that's something that I try to describe for my specific case that I'm thinking about index and something. To answer your question, not answer your question, but to add to my answer to your question, in these works that I mentioned, you can actually see how they associate a cubic ring to a cubic form by writing their multiplication table. If you have a cubic ring, all you want to know is that what happens when you multiply two generators, right? So they actually say, here is the form, and if you start with this form, cubic form, you will have this multiplication table in your cubic ring, and that's how it's just defined based on the coefficients of your form. And if you work instead of if you work with a form that is equivalent to this, it's as if you are working with different omega and theta in your cubic ring, that a different basis in your cubic ring. So it's a very they call it natural. They keep calling it natural, but it's very clear bijection between your multiplication in your ring and the coefficients of the binary form. But this bijection is quite powerful. Of course, it covers everything that I explained today. So not only that, that it just translates something like an algebraic structure like a ring to binary forms, and everything is in terms of discriminant, but everything is can be seen in terms of the coefficient, but lots of properties and invariant theory of that is, like, for example, I'm not talking about invariant theory much today, but the discriminant is something that is preserved, so you can tell what the discriminant of your ring as a ring is by just computing the discriminant of your binary forms. You don't even need to have the basis for your ring to be able to compute that, and so on. And there are lots of other nice properties. So let's see what we are. I am officially over time. I started a bit late, but I'm gonna end by this result, but I don't want you to be bothered with the technicality of that. So the result of myself that I wrote here is that I wrote it here for cubic, but generally I proved for Thue equations that if you have a Thue equation and you have f of x, y equal to m, if this m is small enough, and by small enough, I gave the relation here, but I look a little bit complicated, don't worry about it. All you need to know, if it's small enough in terms of the discriminant of the form, then you don't have to factor in the prime factors of M. You can have a bound, an upper bound for the number of solutions to this equation that only depends on the degree and not the prime factors of M. Remember, in the Bombieri and Schmidt case, f of x and y equal to M had C times D solutions at most, but then for equal to M, we had to have d to omega of M coming in. So what I'm saying in this kind of result is that M doesn't have to be 1, but it has to be a small in terms of the discriminant, right? And this result was proven for general Thue equations in terms of cubic. I translated here. But this beautiful bijection that comes from the work of Dilone, Fadiev, and others that I mentioned gives us something about the monogenic rings, and that is that if you are in a ring of integers and your number field, your cubic number field has discriminant D, then you can count the number of monogenic subrings that have a small index. And those are of course finite, but then I can, with this theorem and these bounds, I can give a constant how many subrings of a small index we have. So that was the nice thing. I want to go very quickly through a couple of things. So this slide I mentioned before, we proved a more general result, but for binary cubic forms, we proved that many Thue equations, cubic Thue equations of this form have no solution. And by this correspondence that I talked to you about, what I get is that right away we get that a positive proportion of monogenic orders or monogenic rings are not, a positive proportion of cubic rings are not monogenic. And that just comes easily from this correspondence. I said, I want to end with this result that I say that all I talked about was monogenic rings, but the big question is about number fields. Is like a random number field monogenic or not? That's the harder question. And the reason is that when I talk about this correspondence between binary forms and cubic rings, these are rings. So it's very hard for me to say what binary form gives me the ring of integers. So our results with Bhargava that I said in the previous slide cannot be applied to number fields. And there is a more recent result by Bhargava and other collaborators that they actually use totally different method, not Thue equations, to say that most of cubic fields are not monogenic. And again, all of these results can be improved because we conjectured almost all of them are not monogenic or so on, but the proportion we get out of this is smaller than what we expect, but those are the first time we could prove that most of them are not monogenic. So let me just end with this. Thank you so much.
Thanks a lot for your very excellent talk. And anyone can ask a question. If there is no question at the moment, I have a simple question, I think. At slide 17, you introduced a notion. Yes.
Yeah.
Does matter the discriminant of OK to be a square or not? I mean, is there any difference between the Galois and non-Galois case for cubic field?
The Galois non-Galois case I can't answer you, but I can tell you that a number that can appear as the discriminant would be a square, because at least with the way I define that. So so what I tried to do, I rewrote this formula to get I of x. So if you, so I got that notion that we talked about from this formula. So in this formula, I
Yeah.
of x to xn are, I mean, it's not clear to you. You can say definitely as a form, this has, if you do, but it's a simple routine calculation, you see that they come from all these conjugates, the coefficients are symmetric function of algebraic conjugates. So they are going to have integer coefficients. So basically, if I write, I took this and on page 17, I rewrote that this way. So these numbers naturally would be, everything that appears here would naturally be an integer, but then you have, by the way, I mean, at the very end, everything would be an integer because the coefficient of these are coming from this conjugate. So that's what it matters to me. But what I'm trying to say is that these relations just work because of that formula, but it doesn't really tell you what numbers are eligible to be the discriminant of OK or so on. But once you work with a fixed number field, just by simple calculation, you see that the f of x and y that I introduced here would have integer coefficients, and that's just because this alpha I and beta i's are in this number field that had discriminant OK. I don't know if it's a convincing answer.
Okay. Thanks. I
My
see.
simple answer is that this formula is not, the way I wrote it here is not that deep. It just came from this identity,
Yes.
but by no means it can answer the question of what number can be the discriminant of
Yes. Yes.
a number field,
Thanks.
and it doesn't see anything about the Galois group of that number field.
Thanks. And I have another question. In your last results, the term epsilon should have any condition?
Epsilon, so yeah, I tried not to read that. Epsilon should be, so what the result is trying to say is that you got to take the exponent of the smaller than 1 over 8. You cannot get it 1 over 8, but it has to be a smaller than 1 over 8. But any value of positive epsilon that is between 0 to 1 over 8 would do it. So this is for you, you don't see the use of this, but this can be helpful when you actually want to have explicit results. For example, I think in the next slide, I tried to write an explicit result and I took my epsilon 1 over 16. So when you want to optimize like how big or small you want your discriminant to be to work with, and then.
And sorry, and the upper bound 1 over 8, where does come from? And why there isn't 1 over 8?
There is good reason for that. In my result, when I worked that out, it was coming from my approximation, because here I'm replacing 1 with m, and when I do this Diophantine approximation of, like I told you, the main idea of 2x over y gives a rational approximation close to alpha I. So when I do approximation and I want to prove that these are good approximations and therefore there can be that many rationals, my m has to be small enough so that it kind of get canceled with the discriminant that naturally contributes. That's methodology. That's what comes from the method, right? But there are geometric reasons that maybe I attempt to explain to you. So if you consider the curve f of x and y equal to 1, the discriminant of f says something about this region, or that it's created by that. So again, I'm very vague, but you are thinking of something, some curve, and it has a volume, and so the discriminant talks about the volume that this has on the plane, let's say, right? Okay, so and somehow you are looking at this volume that f equal to 1 gives you. But once you leave this a little bit, you can basically generate more integral forms of x and y that are integers outside. So when you are doing your analysis, let's say, you have to, in order not to have too many solutions that your m contributes to that, you have to be careful not to leave that volume so far. What do I mean by so far? So that you don't allow any integer points to occur. So that difference is how far I can get from this region that is defined by f equal to 1 and has the discriminant in it.
Thanks for your perfect answer.
Sure.
I got it.
Great. I'm
Thank you.
happy.
Thank you so much.
Thank
Was
you.
excellent, sir. And
Thank you.
anyone question?
I also have some questions. So, can you say a few words about the proof or the method of the proof of the last two results you mentioned?
Which
This one and the one with Bhargava.
Okay, the one with this one that we were just talking about is purely Diophantine approximation, and as I said, it's I did use linear forms and logarithms in that, which is a more elaborated method of Diophantine approximation. Today, I only talked about Thue's result, that there are finitely many x over y close to any algebraic numbers and so on. But then Baker and then other people worked on these linear forms and logarithm that is a little bit more complicated, elaborated, and so on. So that's the method. The method is basically, is simply here, is to find technical way and try to be smart, not waste too many x over y and count as few as possible. And if I want to call it a mathematical approach, it's mostly analysis. Okay. But then the result with Bhargava definitely uses that sort of result that I talk about, f of x and y equal to m. So we want to prove that several things like f of x and y equal to 1 do not have solution. So we used my result that if you choose an m that is small in terms of the discriminant of this, you get a bound that is of the form c times d. And c can be explicit and d is the degree of your form, right? And then we said that let's just talk about m being like p1 to pk, and we determine them later. And then what we did, we reduced them the way that I tried to describe in Bombieri and Schmidt. But in order to have these trees that I made here complete, we have to choose the form such that it completely splits mod p1, it completely splits mod p2, and so on. That part of the work comes from arithmetic statistics, lots of things that Bhargava has done with the arithmetic statistics, and like the probability that a form splits mod this prime, and then like how they are connected. So anyways, we kept reducing this till we got bunch of form like g1 equal to 1, g2, that would be d omega of m, which in my case I have k prime here, and equal to 1. However, my result says that if m is small enough, this has only c times d solutions. This reduction says that the solutions of these have to correspond to uniquely to solutions of one of these equations down here. But the idea here was that we created, we created d to omega of m, which is d to the k here, forms equal to 1 up here, but my result says that this has c times d. So c times d, as soon as you had c times d is smaller than this, so you would know that there got to be some of these equations with no solutions. So this work was a combination of my work, which is the Diophantine approximation, a lot of things coming from arithmetic statistics. As I said, you have to make sure your form splits so that completely mod each of these forms, so you get as many as you can. And then you have to make sure you have forms with big enough discriminant. That's not hard. Like forms with bounded, there are finitely many classes of form with finite discriminant. You have to make sure when you are creating or constructing these forms, you don't create local obstructions. So those are coming from more, as I say, what's called these days arithmetic statistics, but more classically geometry of numbers.
Great, thank you. If I may ask another question. So I'm trying to package two questions in one. So for you, the next step is to improve these results or these approximations, or to extend it to higher degree number fields, rings?
For me, the dream is to improve the bounds that we have in this result, like because we got a positive proportion, but it's very small. We believe that most of two equations have no solution. But this is really dream because it's a very difficult one. But if you're asking, this would be a personal question, I would say what I'm going to do next, but that's what I'm doing now, that to use Thue equations to talk about monogenic rings in higher degrees. But it's not obvious because right away when you write an index form equation, it has more than two variables. So it takes a little bit of more work to reduce
great.
them, and quartic is certainly the next one.
But it's very hard, I guess.
It is hard, yeah. But with quartic, there are some results, and actually very recently Bhargava put a paper that explains more of the relation. But yeah, I'm working more on a classical point of view, so I think that I have a little bit of writing, but for quartic, the reduction takes a while, but we don't have ideas for past quartic, so that's going to be the hard work. But I think that's mostly the hard work. But like the one that I said for the representation of integers or so on, that's more, it really requires new ideas, I would think.
Great, thank you very much. Thank you.
Thank you. Thanks.
Sorry, there is another question in the chat box from the host. I don't know who was the host. I think it's me. He or she asked, is there any explicit algorithmic method for solving Thue equation like in Magma or Sage?
I'm not the right person to answer this, but the short answer is yes, Magma does it, Perry does it. I think Sage probably uses Magma to do it. But they don't, like, you can't just give any Thue equations to solve that. So of course the coefficients and therefore the discriminant has to be bounded. For example, I do know Mike Bennett and and one of his collaborators, who's not a number theorist, but they do a lot of computational work together. They are working on just pushing the computational methods to get to solve more Thue equations. So yes, there is, but you can't just give a random Thue equation and solve it. It just has to have a small discriminant. But what people who are doing computational things are pushing for, like, they are trying to be as smart so that without like bigger computers they can do more like larger discriminant and so on. But if I could not see the question actually, but if the question is more about a direction of work, I definitely encourage people to, if you have your hand in computations, you're in a good position. I definitely encourage you to do that. We need people to do more of scientific computation with that.
Thank you very much. If there is no question.
Actually, I have a question. Actually, I haven't done my homework on this question. I haven't searched for it. But this conjecture that you said that you expect a zero, like density zero monogenic cubic fields. Is it for general? Is it also conjecture to be zero density for other degrees?
I think so. Yeah, I think so. But whatever conjecture means, yes. But I haven't worked for very long in this field to have my own feeling. But my understanding is that yes, actually, when you have higher degrees, so it's harder. So I think it's harder to find a monogenizer. So I do think that it's for higher degrees too. For number fields, Bhargava and collaborators that I wrote, like Alpo, and Schindman have results both for cubic and quartic, and they came out 2020 and 2021. So they're very recent, very elaborated techniques, really beautiful work. But my understanding is that the reason we don't talk about higher degrees is just they're very difficult, but the conjecture holds.
I see. And a very special subclass of them, the ones that the discriminants that are square free. Have we been able to prove that the square free discriminants have density 0 for general number field or for cubics?
I think I shouldn't talk about this, and the reason is that I have seen results, but I do not remember what they proved. There are other special cases. For example, something that I should mention in when I talk about monogenic, cyclotomic fields are monogenic, right? And there are pure cubic fields that there are lots of results about them, and they are monogenic. But so then some people, when they work, they try to prove that these families that we know to be monogenic, they are not dense at all, they are very thin in the whole space. But
Right.
with your specific question, that is a great question. I am actually embarrassed to say that I forgot, but there are work there.
I see. Okay.
But I don't think we have the ultimate answer there. Sorry, who was talking to me? I can't see your.
Yeah, sorry, this is Ali Rajai.
Oh, hi. Yes.
I don't have.
I guess,
sorry.
but I couldn't see. No worries. No. I was asking in case, because I'm having trouble to think about things. I was asking in case I see something, I can forward it to you. That's what.
Okay, great. Then I'll write you an email if you find something.
Oh, that would be great. Yes.
Okay. Thank you very much.
Thank
Excellent
you.
talk. Thank you.
Oh, thanks. Sorry, was there something else in the chat? Oh, thanks. Thank you.
Thanks again. And if there is no question, you may unmute your microphone and join me to clapping Professor Akhtari for her excellent talk.
Thank you so much. It
Thanks
was
a
very
lot.
nice to see you. Thank you, everyone, for being here. Yeah.
Nice to see you too. And thanks again. Thanks for thanks to have a talk in our seminars.
Of course. Yeah, of
and
course. That was
thanks
a pleasure.
everyone for attending. And I hope to see you for the next seminar where Ali Mohammadi will talk there at 2 weeks from now. And okay, I stop recording and bye-bye everyone.
Bye.